Welcome to part 3 of the webinar series on securing IoT applications using Mbed TLS. My name is Hannes Czefenik and I will guide you through this webinar about random number generators. So why should we talk about random number generators? In the first two webinars I had shown how to use the Keil MicroVision 5 IDE to configure applications for use with the Mbed TLS middleware. In those two presentations, I had stressed the importance of using a hardware-based random number generator, and I listed also a few examples of where implementation mistakes or wrong design choices can lead to security problems. You can watch a video by Paul Becker about entropy requirements in IoT on the Arm Mbed YouTube channel if you are not familiar with the random number generator usage. Those who carefully watched my talks may have noticed that I had actually cheated in my example code. The code did not use an RNG due to the settings in the Mbed TLS_config.h file, and particularly those that are listed here: no entropy, sources, and test null entropy. And this led to a compile time warning which said this build is not suitable for production use. We glanced over these warnings. But today we will enhance our code to make use of a hardware-based random number generator. We are still using our Keil development board with the STM32F407IG MCU. So important question is obviously whether this MCU actually supports a hardware-based random number generator. And normally we wouldn't start looking at the hardware features after the hardware is already sitting on our desk. Luckily, in our case, this MCU supports a hardware-based random number generator, and so we are going to make use of it. But in general, how good is the availability of such hardware in modern MCUs? And it turns out that it's easy to find MCUs with a hardware-based random number generator, and I provide here an example. Using the SD-provided MCU Finder tool, you can see that there are 410 MCUs that support such a hardware-based RNG. So this is clearly not an exotic feature or something that requires a dedicated chip on your PCB. To access the RNG, we need to understand our hardware a bit better. Of course, the explanation that follows is specific to the SD implemented RNG and may be slightly different with other vendors. The underlying principles are, however, the same. If you are an embedded system developer, then you're most likely familiar with the way how to talk to various peripherals on your MCUs. If your background is more in security, then you may need to get some help to get started. The STM32F407IG product webpage contains a number of manuals, and we will have to become familiar with the relevant parts. Section 24 of the reference manual describes the RNG functionality. In a nutshell, it says the following. The RNG of this MCU delivers a 32-bit random number with every access. The peripheral is attached to the AHB2 bus and is memory mapped. Memory mapping peripherals is a very common technique in the ARM architecture, so that shouldn't be a surprise. The RNG on this MCU can operate in two modes, in an interrupt-driven mode and in a polling mode. We are using the polling mode. You can easily modify the example to work in the interrupt mode as well. And probably most importantly, there are three registers dedicated to the use of the RNG. There's a control register, CR, a status register, SR, and a data register. So this is a picture taken from the reference manual. It shows the three registers we are using, and I highlighted the relevant bits that we are going to use in red. Starting at the bottom, the data register, this is where the random number is located. The status register indicates a number of, or has three bits that are relevant for checking for errors. And the control register has one bit that we use to enable the RNG. The other bits are used in interrupt modes, and most of the bits are reserved. So the steps for accessing the RNG are fairly straightforward. First, we have to enable the RNG. And in this case, this is done using the RNGN bit in the control register, which we just mentioned. There's a small note in the reference manual that says that the first generated number after setting this bit should not be used according to the FIPS publication 140-2. So this is something to keep in mind. Once this peripheral is working and we want to get access to our random numbers, we then need to check for errors. And we also need to determine whether the data and the random number is actually ready. And there are these 3 bits that we can use in the status register to determine whether there's a seed error, whether there's a clock error, or whether the data is ready. And then if there's no error and the data is ready, then we can actually read the random number. Also noted in the manual is that each generated random number has to be compared with the previously generated number. If the test fails and the 2 numbers are equal, then an error occurred. So this is also something we have to take into account in our code. So with this know-how, we are ready to test out the RNG hardware and see whether it's actually working or whether we properly understood the reference manual. So since we now know what registers we want to look at, I opened STM32CubeMX, since it's a good way to write a test program to become familiar with the hardware and actually to know whether we properly understood it. So if we can't get the RNG working in our test program, then it makes no sense to play around with a more complicated application. So let's generate a new project, and we select our MCU, the STM32F47IG. Found it already. And this is also a good way to get access to the documents, the reference manuals, data sheets, and so on. But we looked at that already. So this is our MCU. And all we need to do here is just to activate the RNG peripheral, nothing more. And that's enough to generate the code already. So let's give it a name. Test my RNG. And then we also need to indicate that we want to generate the code for the MicroVision 5 IDE. And I only want to copy the necessary library files rather than everything. Normally we could include all sorts of configuration options here for the peripheral, but in this case we don't. I only want to have the code included in the main rather than separate files. And that's it. So that was quick. Let's open the main.c file. So there are a couple of interesting aspects here. So CubeMX copied the relevant files and also included the header files that we want to use. It also populated the main.c file with the relevant code for initialization and also with the data structure that we are going to use here. In this case, the RNG_handle type def structure is the structure we are going to use for this abstraction layer that SDM provides. So instead of accessing the registers directly, which we could, we want to make the code more portable, so we use this abstraction layer. And we'll see in a second that underneath the abstraction, of course, ultimately it accesses the hardware registers. But before we go there, let's make sure that the project is correctly configured. I always double check whether this browse information is included so I can actually browse through the code conveniently. I would like to set the optimization level to a lower level so we don't have any issues with the debugging. And I need to reconfigure my debugger because I'm using the uLink Pro and it's correctly recognized, so that's great. So let's compile the code. While it's compiling the code, let's look a little bit further into the code. There's this mx_rng_init, which is the initialization function, which is invoked here right after main to enable the RNG hardware. Let's have a look at it. It's actually here. So here you can see in the main.c it included this function, which is just a wrapper around this hal_rng_init. And if we go in there, we see that the code, the actual code for the RNG HAL is included in this STM32F4XX_HAL_RNG.c, and there's a corresponding header file as well. And what this code essentially does is, here you see a macro. It has this macro __HAL_RNG_enable, which then translates to nothing else than setting the RNG enable bit in the control register, which is the one we talked about a little earlier. And you see a couple of macros defined here. You will also find the function prototype for the HAL_RNG_generate random number here, which we are going to use to actually read a random number. It takes two parameters, the data structure we talked about earlier, and then the result is a 32-bit random number. So let's try this out. Let's create a small structure here. And now we just need to call this function, the HAL RNG generate random number. The IDE already proposes it here. And then we take the RNG_handle type dev structure, which CubeMX already indicated or added to the main.c file for us. And then we write this to our allocated structure, and that's all there is for our example program. So what we expect here is that as we run through the program, this block of memory is allocated with some numbers which appear random. If we go and have a look at the STM provided code here, we will notice that it doesn't actually include any checking for the FIPS specification, which we talked about earlier. So we would have to add that ourselves a little later. So we are going to do that later, but for the sake of this example, we just want to see whether this actually works. Various things could happen if the initialization function doesn't work properly, then we won't get anything back at all, or the whole program hangs, and so on and so on. Start the debugger. We run through the code, and then let's see. So here we have the memory region. So currently it's filled with all zeros. And as we step through, we expect it to be filled with the random numbers 32 bits each time. So you can see it here. So we retrieve the first one, get the second one, and so on. And it looks pretty good. We could also check the registers as well if we want. We could do those. So here's the RNG register. So we can actually see the register content here as well. So here's the data ready, the DRBG data ready. We see no errors here. We see the RNG enabled bit set here, and so on. And then, of course, this is the data register. And so as we scroll through, we get more and more random numbers being copied into the allocated data structure. So in our case, this is exactly what we wanted. So we can be fairly confident that this works. And so then as a next step, we need to apply this to our Mbed TLS example program. Before we go to our Mbed TLS example program and modify to include the RNG support, we also need to look at one topic, namely the NIST Special Publication 800-90A Revision 1. And this publication defines a so-called deterministic random bit generator, or DRBG. This DRBG is a mechanism that uses an algorithm that produces a sequence of bits from an initial value that is determined by a seed. And the seed is this output of a random source. In our case, that would be the hardware-based random number generator. And the DRBG is said to produce pseudo-random bit sequence. And if you look at that figure, which is taken from this NIST specification, it aims to explain the concept. In middle is the pseudo-random function, and it takes various inputs. The most important input comes from one of the entropy sources, our hardware-based random number generator, but there are other things like a personalization string and nonce additional input. This input is then used by the pseudorandom function to deterministically produce a pseudorandom bit sequence. And in our implementation, and the NIST specification provides a couple of options. We use a block-based cipher, namely using AES, since we use AES also elsewhere in our code as well. There's also an HMAC-based variant, which is also specified and which is also implemented, but we just use this one. So what we need to do is, if we want to use this NIST pseudo-random number generator, is to hook in our hardware-based random number generator offered by our STM32F407 into this entropy source of this DRBG. So the consequence is then you get almost small number of bits and bytes from the hardware-based random number generator, which then is fed into this pseudo-random number generator, which produces a much longer sequence as needed for the applications. So let's have a look at how this is then implemented in Mbed TLS. So this is a pretty complicated slide, but it tries to provide an overview of the connection between the entropy accumulator and the DRBG implementation based on a block cipher. So let's start with the left-hand side. The Mbed TLS underscore entropy underscore context is the data structure here that the entropy accumulator uses. And it's used in all the function calls as well. The initialization function is quite obvious, self-explanatory. The most important function here is the entropy add source, which is where we hook in our hardware-based random number generator. It's this one. We will take a look at the parameters in a few minutes, and we'll see how the callback then works to actually use our hardware. And finally, there's a free function as well. We won't use that for now. On the right-hand side, you see the DRBG function, and the CTI stands for counter mode because that's the way how the block cipher is used in counter mode. And similarly here, there's a data structure called CTR underscore DRBG underscore context, which we're going to use in all the function calls. There's an init and a free function. So the most important function here are the DRBG seed and the set prediction resistance, which we will talk a little bit about. And they require some explanation. The DRBG seed algorithm allows us to link the DRBG to the entropy source. So that's an important step to actually link the two implementations together. And then the prediction resistance functionality means that every call to the DRBG causes a fresh entropy to be retrieved from the hardware if it's turned on. So what does that mean? So you have to decide based on security requirements on whether you want this functionality or not. Enabled means that your IoT system will invoke the hardware-based random number generator every time a random number is needed and when the DRBG is rerun, then subsequently with this new seed value. If it's disabled, then the random numbers produced by the pseudo-random number generator are utilized directly without going on and talking to the hardware every time. So it really depends on your needs. So if you're concerned that an attacker might get access to the data stored in RAM for use with the pseudo-random number generator, the data structure that is described here, the DRBG context structure, may be accessible to an attacker at some point in time. And so if that's a concern and you're worried about this internal state to be exposed to the attacker, then you should enable prediction resistance. Finally, what we also need to do, which is here at the bottom, we need to create a link between the DRBG implementation and Mbed TLS via the Mbed TLS underscore SSL underscore conf underscore RNG function. This registers a callback. So we basically then manage to link up the Mbed TLS with the DRBG implementation with the entropy source. And then with this knowledge, I think we are good to go to have a look at the Mbed TLS example code and see how we can configure it. So I've now opened already the example program from last time, from the last webinar, where we used the public key crypto example. And we're going to enhance this to support the random number generator. So the first thing we need to do is we need to manage the runtime environment, because we now are not going to use the CubeMX anymore. We could theoretically, but in this example, I think this is simple enough in terms of peripheral use that it doesn't make sense. So all we need to do here is we need to go to device STM32 CubeMHAL and enable the RNG functionality. That's it. We'll take the initialization code to enable the hardware. That was the code we had already running in our previous project, so we just copied over here. So this is our example code from previous hands-on, and we just include it. Let's copy it in here. We need to get rid of that error handler because we are now using the Mbed TLS functionality instead. And what we also have to define is, or declare, the RNG underscore handle type def structure, because otherwise this structure will not, the instance will not be recognized throughout the program. So we'll just do that here as well. The next thing we need to do is we need to go to the Mbed TLS underscore config and change RNG settings there as mentioned initially. So we have a couple of them already. So the first one in here, no platform entropy. We want to leave that in there because we are not using any, or our platform, our operating system doesn't offer concepts like /dev urandom. So we have to provide it on our own. We also want to have our own entropy code, which is the next one. That's why we want to have it in there. We also want to make use of the DRBG based on counter mode AES, which we talked about previously. So we want to include this one as well. The HMAC DRBG is something we don't need for this purpose, but if you recall, for the public key crypto, we are using the deterministic ECDSA, and so for that, we are actually using the HMAC DRBG. So we leave that unchanged. The other two calls, obviously, or these other two preprocessor directives are not needed, so we just get rid of them. Okay. What we now need to do is, here you also see, which we already previously used, we used the device unique personalization string for the DRBG. So we had that one configured already. And we have also previously already configured the data structures, or initialized the data structures, the entropy context and the DRBG context. What we still have to do is we have to initialize the RNG itself. So let's do that. So we enable the RNG functionality. And then we also need to include the entropy source. So as mentioned, we need to provide in the entropy context. And then we need to provide the function, a callback function, which we still have to write. Let's call this entropy poll. And then as a parameter that function, we pass in our data structure for the RNG, because the function will have to access that data structure to get access to the actual random values and so on. And then we also have to indicate the length of the buffer that we allocate for this data. And the length depends on the type of hash function being used. For SHA-256, the buffer length is 32 bytes. And for SHA-512, it's 48 bytes. So we just use a parameter here, namely DRBG entropy len. And then finally, when we add entropy sources, or in our case only one, we need to indicate whether this is a strong source or a weak source. If we provide multiple sources, we have a mixture between strong and weak. But if we only have one, or in any case, we need to provide at least one strong source. In our case, we can claim that this is a strong entropy source, not only because we trust ST Microelectronic for what they did in their hardware, but there's actually a separate application note provided by SD where they explained how they passed the tests, and you can actually redo the tests that NIST put forward for implementing random number generators. And if this failed, then we are obviously in trouble. So now we need to implement this actual function similar to what we did in our example program. We have to now access the RNG and to retrieve the data. So I have already prepared this function, so we don't need to write through it now. I will explain it to you in a second. Let's put this somewhere up here. So this is the entropy poll function. We have to provide 3 parameters into that function. The first one is a pointer to the structure to the RNG handle type def structure, which is the parameter we pass in there, which allows us to get access to our RNG. Then output is a buffer, and it's a buffer of a given length, namely the length that is indicated as mentioned earlier with the size that was allocated for that buffer. It's actually 4 parameters, sorry. And then finally, OLEN is a return value indicating on how many random bytes we actually created and placed in this output buffer. So here, probably the most important part is in this function is that I added the error check handling as well. So I check for, as mentioned earlier, I check for the seed errors, I check for the clock errors, and I'm using the macros that the SDM guys provided as part of this hardware abstraction layer. So I use the __hal _RNG _get flag, and it checks whether the seed error bit is actually set or it's not set. The same is with the clock error. So every time I go through here and invoke this function, I check whether there's any error. And also the RNG get random number, that does the check for me already whether the data is ready. So I don't have to do that check myself again, but I need to do the other checks. What I also included in this example program is the recommendation from the FIPS publication to actually check for whether 2 subsequently retrieved sequence numbers are equal or not. And I also dismiss or discard the first random number that is retrieved after the hardware-based random number generator is enabled. Here in this specific function, I actually discard the first random number every time I invoke this function, which is not necessarily needed, but I did it nevertheless anyway. So I fetch all these numbers, and once they are retrieved, those are passed over to the DRBG, and then further random bits are generated. So this is all the function does, and it should be fairly obvious to you, particularly since we just looked at the example program, which at the core retrieved these random numbers using that high-level function, the generate random number function. There's just a few additional checks around it. And then finally, we need to do one more thing. We need to make a decision about the prediction resistance. Let's add prediction resistance as well. Set prediction resistance, and we again need to provide the context, and then let's decide that we want to enable prediction resistance for this code. It's actually the default value is off. This is all we need to do. or to get our code enhanced to support a hardware-based random number based on our platform. So if we compile this, the warnings that we previously had are actually gone, and now our Mbed TLS code would use the hardware it's running on. In a nutshell, not that many steps. Of course, you need to adjust them for your specific hardware. But to summarize here the steps, we had to add the entropy source. We link it to a function a callback function, where we actually implement the access to the hardware-based random number generator, which is what we did. And then we enable we decide whether we want prediction resistance or not. So we enable it or disable it. And the previous code already had the functions in there for initializing the context and also for instantiating the data structures. So we didn't need to make any changes. We included the support for the RNG in our code, which was fairly easy thanks to the UI and the wizards that MicroVision 5 offers. And then we are good to go. To wrap up this webinar, I hope you understand that random numbers are really important for security. Pick the appropriate hardware for your task. And in our case, for a security application, you need a hardware-based random number generator. Use your favorite MCU and follow the steps to integrate your RNG into Mbed TLS. I wish you a lot of fun.